In today's functional analysis class, we discuss open map. So first we define open map. A map F from X to Y, where X and Y are matrix spaces. Y are matrix spaces, is said to be open if for every open set E in X, its image f of E is open in Y. So this is the definition of open map. We write a note. You know that a map F is continuous if and only if for every open set E in Y, its inverse image F inverse of E is open in X. So we prove this theorem, theorem 10.4 in your text. Let X and Y be normed spaces and F from X to Y be linear. Then F is an open map if and only if there exists some gamma greater than 0 such that for every Y in Y, there is some X in X with f of X is equal to Y and norm X less than or equal to gamma into norm Y. In particular, if a linear map is open, then it is surjective. So we prove this. Let F be an open map. And since Ux 01 is open in X, f of Ux 01 is open in Y. This is because f is open. Since f of 0 equal to 0, this belongs to f of Ux 01. There is some delta greater than 0 such that Uy 0 delta closure is contained in f of Ux 01. Consider y in Y and Y not equal to 0. Then we have norm of Y by norm Y is 1. Therefore, delta into Y by norm Y belongs to Uy 0 delta closure. Hence, there is some x1 in Ux01 such that f of x1 equal to delta into Y by norm Y. This is because delta into Y by norm Y is contained in Uy0 delta closure and Uy0 delta closure is contained in f of Ux01. So there exists an x1 in Ux01 such that f of x1 is equal to delta into Y by norm Y. Let x equal to norm Y divided by delta into x1. Then f of x equal to f of norm Y divided by delta into x1. And since f is linear, you can take norm Y by delta outside into f of x1. So this is equal to norm Y by delta into f of x1 is delta into Y by norm Y. So this is delta into Y by norm Y. So you are getting this as Y. Therefore, f of x equal to Y. And norm of x equal to norm Y divided by delta into norm x1. This is less than norm Y by delta since x1 belongs to Ux01. So its norm will be less than or equal to 1. See, let gamma to be 1 by delta. Therefore, norm x is less than gamma into norm y. That is f of x equal to y and norm x less than gamma into norm y for some gamma positive. Thus, if f is an open map, there exists some gamma greater than 0 such that for every y in y, there is some x in x with f of x equal to y and norm of x less than or equal to gamma times norm y. So this proves one part. Now we prove the converse part. Conversely, assume that for every y in y, there is some x in x with f of x equal to y and norm of x less than or equal to gamma times norm y for some gamma positive. Consider an open set E in X and X naught belongs to E. We are going to show that the map F is open. Then Ux X naught delta is contained in E for some delta positive because E is open. Let Y belongs to Y with norm of Y minus f of x naught less than gamma by, then by hypothesis there is some x in x such that f of x equal to y minus f of x naught and norm of x is less than or equal to gamma times y minus f of x naught. Since y belongs to y and f of x naught belongs to y, y minus f of x naught is an element in y. Since for every y in y, there is some x in x with f of x is equal to y and norm x less than gamma times norm y for some fixed gamma greater than 0, we can apply the result for y minus f of x naught. So, since y minus f of x naught belongs to y, there exists an x satisfying this condition. Then, since f of x is equal to y minus f of x naught, then y is equal to f of x plus f of x naught. So, this is f of x plus x naught, where x plus x naught belongs to ux x naught delta, which is contained in E. This is because since norm of x is norm of x less than or equal to gamma times norm y minus f of x naught and norm of y minus f of x naught is less than delta by gamma. So this is less than gamma into delta by gamma. So this is equal to delta. That is, norm x is less than delta. Norm x less than delta implies x belongs to u x0 delta. So this implies x plus x naught belongs to u x naught delta. So this is the reason. Thus, uy of f of x naught delta by gamma is contained in f of e. Therefore, f of e is open. Therefore, f is an open map. So this proves that theorem. So that's all for today.